your screen and start the talk.
Okay. Okay. Can you see the slide?
Yes, we are seeing a slide. Rather, we are seeing the PowerPoint window.
Okay.
So yeah.
Yes.
Okay, now we see only the slides.
Okay. Thank you. Oh, sorry. Yeah. And now can I begin?
Yes, please.
Okay. Good afternoon, everyone. I'm Congcong Le. I will be new postdoc in RIKEN iTHEMS. You might research my work on theoretical study in condensed matter systems, including topological systems such as topological insulate, dielectric metal, and Western metal, and unconventional superconductor activities. Now I am interested in twin layers and topological physics in the non-formation systems. Today, I will talk about the basics of topological band theory. Next slide, I will talk about crystalline materials. In condensed matter physics, we focus on the crystalline materials with periodic structures. These crystalline materials can be classified into semiconductor, insulate, semimetal, and others. So in order to explain this interesting phenomena, we need two steps. The first steps, we need to get electron Hamiltonian. And the second steps, we need to solve Schrödinger equations like these formulas. So in here, E is electron energies and phi is wave functions. If we know electron energy and wave function in principle, we can understand everything. So then I will explain how to get single electron Hamiltonian from crystalline materials. Yeah. Okay. In here. This slide about electron Hamiltonian. A crystalline materials can include so many nucleons and electrons. So then we can get total Hamiltonian like this formula. The first term is electron kinetic energies. This term is similar to classical formula. This is kinetic. Also, this is the velocity and m is mass. So the second term is interactions between electrons. It also is similar in classical formula like I minus J equal Q1, Q2. This is electron charge. So another two terms is about the nucleus kinetic energy and the interactions. The last term is the interaction between nuclear and electrons. So if you say this total Hamiltonian, maybe you feel it's very complicated. So in order to get single electron Hamiltonian, we need to take some approximations. So the next slide, I will give some approximations. Okay, the first approximation is Born open Hammond's. It means the nuclear motion is so much slow than electron motions and they can be considered to be fixed. So we can separate nuclear and electrons. Then we can get the electron Hamiltonian like this formula. This formula compare with the last slides. We ignore the nuclear the kinetic energy and the nuclear the interaction. So in here there are only 3 terms. The first is electron kinetic energy, and this is interaction between electrons. The last is interaction between electron and nuclear. So the second is the independent electron approximations. It means we approximate the electron and electron interactions, and then we can get the single electron Hamiltonian like this formula. So we can say the first kinetic energy, and this one is the interaction between electrons. This interaction between electron and the nucleus. So the next approximation is a periodic perturbation. It means we take the interactions, write this one, we call VR. Then we assume the VR has periodic like this. So finally we can get the single electron Hamiltonian and Schrödinger equation with the periodic partition, like this formula. This is single electron Hamiltonian. This is single Schrödinger equations, and this perturbation has periodic. Then, if we consider the periodic, the wave function can be read like this one. It has plane waves forms. Then, if we put this wave function into the Schrödinger equations, then we can get moment space electron Schrödinger equation like this one. So based on this equation, we can get electron band structure in the moment space. Then next, I will give some example how to get the band structure. Yeah, so the first example is about one-dimension hydrogen change. This is simple case because here is hydrogen atoms. So in this case, only one electron, and the electron is in the s orbital. So in order to solve Schrödinger equations, we use the atomic orbital to construct block wave function like this formula. Yeah. In here is atomic s orbital, and also then we can put this wave function into Schrödinger equations. Finally, we can get like this one. So, and then we can do some derive and get the energy like this. This energy is this k x k is in the moment, so we can get the band structure like this. In here, epsilon 0 is the onset energy, and T1 we consider the nearest hopping term. So in here, this is the first examples. The last example I give graphite. Yeah. Because graphite has sp3 hybridization, so the only one electron in the pj atomic orbitals. So we can use the pj atomic orbital to construct block wave functions, and then because the unit cell like this, it has two atoms. Every atom can give pj orbital. So in the band structure has two bands like this band structure we can get. It's one band, another band, and in here it's formular in here. Yes. So and the gamma m is from moment space like this brain zone. So this is about the graphite band structure, and then I want to explain. Okay, I want to explain insulate metal and semimetals based on the band series. We can see the first band structure like this one. If Fermi level in the band gap like this, so in this case, the no electron can provide the any transport informations. So in this case is insulate. And then if Fermi level close the band, so in this case they have like this electron can provide transport properties. So in this case is metal. The last case, if Fermi level cross the point, so because the Fermi level is a point, so this we call semimetals. Okay, and then I want to give some of how to know that a crystalline materials is topological true or non-true. Also, there is two steps. The first one, we need to know if there is band inversion in the band structure. It means like this picture. If the conduct band is from s orbital and the valence band from the p orbital, then if we change the parameter, maybe the conduct band is down and the valence band is up. Yeah. Then in cross open gap. So finally, we can get this band structure. We can see the s orbital and in the valence band like this, and the p orbital is in the conduct band. In this case, we call band inversions. So if we have band inversion, then next we need to calculating topological imbalance to confirm this material is topological trivial or non-trivial. If it's non-trivial, we call topological insulate. And then if we cut y direction in the real space, yeah, and the x direction is periodic. So we can say the edge state like this. This case spin Hall effect. So is this direction is spin up and another spin down current. So this edge is the same. So and next I want to give example. So yeah, before talking the example topological semimetal couple iodides, I want to review atomic electron configurations. Atomic orbitals depends on three quantum number. It's principal quantum number n, and angle quantum number L, and the magnetic quantum number m. So like this table, if n equal 1, the only s orbital because L equal 0, like this. If n equal 2, L can equal 0 and 1, they has s orbital and 3 p orbitals. So, and also for every atomic orbitals, the maximum field number of electron is 5L plus 2. It means s orbital can have 2 electrons, and the p orbital is 6 electrons, and d orbital is 10 electrons. So if in a crystallized materials, if every atomic orbital is fulfilled, this material usually is insulate, semimetal, and or semiconductor. So next slide I shows couple iodides case. So the first we can see the element couple and iodides. We can say couples electron configurations like this. The only for s orbital not fulfilling, another spd orbital is fulfilled. And iodized electron configurations, the only p orbital not fulfilled, another orbital is all filled. So then these two elements form materials couple iodides. We can get the couple iodides valence is +1, and the iodides valence is -1. Then the couple iodides +1 electron configurations like this, and iodides -1 configuration like this. So we can say the all electron orbital fulfilled. These two there, because the couple s of 1 give iodides. So in this case, couple iodides should be an insulator or semimetal or semiconductor, and also from this information we can get the band structure like if formula in here, because because the s orbital is 0, so the s orbital band should be up the formulas. Because the p orbital are fulfilled, the p orbital band should all occupations like this. Yeah. So next we check band structure, this materials. Okay, like this. Yeah. In this band structure, the red is a p orbital band, and the s blue is couple s orbitals. We can say the s orbital band most is upper formula, and the only one is below the formula, and the p orbital almost occupations below the formula, and the only little is above Fermi level. So in this case, in here is band inversions. And also in here, band inversion in here is a close point, like this. This point is protected by symmetries. So we can form the band inversions between s orbital and p orbital. In principle, next we need to calculate the topological invariant to say if the material is trivial or non-trivial. And in here I just shows band inversion, so don't give the topological invariant. And this paper gives the topological invariant is non-trivial. So in this case is a topological semimetals. That's all. And yeah, I give all example. Thank you.
Okay, thank you very much for very pedagogical talk. And I have to apologize. I have misunderstood the pronunciation of your first name. So could you repeat that? How you can pronounce your name?
Sorry,
Yeah, but your name pronunciation. I thought from the English writing.
Yeah.
So it's rather Tsung.
Okay. Yeah, maybe this case, this is not Kong.
Okay. Sorry
yeah.
about that.
Okay, that's okay. Yeah. Chongchong.
Changdan. Okay.
Yeah.
All right. So now questions. How do?
Yes. Thanks very much for your talk. Yeah, I'm in nuclear physics, so I may ask two outsider questions. Sorry for that. So the first thing is you transform the two-body Hamiltonian to one-body Hamiltonian. It seems to me it looks like a Hartree approximation. Is it true, or is it something more about it?
Yeah. So yeah, you're right. So in here I just give the simple explain.
Okay, so this is one of the simplest case, so the Hartree approximation for that.
Yes, in principle, interaction has Hartree-Fock or exchange interaction, many interactions. So I just give simple explain in the case.
Okay. So in practice, you use a more complicated approximation?
Yeah.
Like you beyond Hartree approximation?
Yeah. Also, because this is from the DFT band series, so maybe if the superconductor and another phase contain many interactions, maybe we don't know.
Okay. So the second question is, after you map the system into one-body Hamiltonian, then to solve this one-body Hamiltonian in momentum space is relatively easy in some sense. So then what would be the most challenging points for the study? Yeah, because a one-body problem would be easy, right? But
yeah.
So then what would be the challenging points?
Yeah. So I don't get me. So you mean how to?
No, I mean after you get this one-body Hamiltonian, to solve it is relatively easy, no matter numerically or analytically, probably numerically. But still, I mean, this field is so hot, and then a lot of researchers are working on this field. So I would like to understand then what is the key challenge instead of solving, instead of solving one-body Schrödinger equation.
Key challenge. So maybe in principle, we can get the band structure from the the DFT or another software, and usually then I can get the no interactions topology models, and then we can hence add the some interactions and do another another mesh to deal with the interactions like RPA or another RG message.
Okay. Yeah. Thanks. Thanks. Yeah, we can discuss more later, I guess.
Yeah.
Yeah, please.
A related question or something related to the audience question is that probably just solving the one body is not that difficult, but finding out whether it is topological or not is a different matter, right? If I understand it correctly. So there's another step beyond just by solving the one body. Is it? Am I understanding you correctly?
Yeah. The topological phase beyond the conventional band structures.
Mm-hmm. Okay.
Yeah.
So this is somehow, beyond just solving the one body problem, right?
Yeah.
I think it is the answer to our job, maybe.
Yeah. Sure. Yeah. But we also can get some uniform information from the conventional band structures. For example, like span dimensions. Also, then we can calculate topological invariant, confirm this topological or not.
So maybe the related question is, so this one body Hamiltonian contains all the information of this, all the information of the topological nature of the material, or do you need some special boundary condition or something, or who knows? I mean, is this one body problem knows something about the system is topological or not, or do you need some extra input?
You mean if we focus on the no interactions topological and the single electron Hamiltonian can give all informations, and we can get the wave function, and then based on wave function we can calculate the topological invariant, and
okay, so this one body Hamiltonian knows everything, including whether it's topological or not. Okay.
Yeah, but this is only for no interactions topology phase, not including interactions topology phase. Yeah.
Okay, so any other questions? Okay, if there's no further
Let me see.
question.
I have one question. It's okay.
Yes.
Maybe related to the question by Hatsuda. But in the transparency, in the second from the last, you mentioned something topologically protected. So in first sense, topological, no, later one, later transparency, not this one, but further on. Could you?
So means that
No, further on. No. Yeah, around here. You said the blue, maybe next transparency, yes.
You mean next or?
Yeah, from that, yeah. If blue is CUS orbital or like that, then you mentioned something is topologically protected. So in first sense protected.
Yeah.
Right? When you discuss after this one, you draw something, and then you mentioned topologically protected, so on, right?
Yeah.
So in first sense, topologically protected, and how it is stable, I know.
Okay. So first, in here I just give the band inversion from the from the band structure like this. And it also we need to calculate the topological invariant and another topological edge state and fermiac and some things.
Yeah, but that means you need more complicated considerations. Just by
Yeah,
looking
yeah.
at this cross around here, say in the left side, that's not enough.
Yeah.
Oh,
Well, I just give little this band structure. I just want to show band emotion, and then maybe I can show. Sorry. Okay. Yeah. I'll talk.
Okay.
Yeah.
It's okay. Yeah.
Okay.
And then
Also you can see this paper and give another.
oh, that's
something.
your paper.
Yeah.
Oh, I see. And then another very naive question is this. Quite often in the Brillouin zone, and if you draw the band type diagram, and when you apply force from outside, people often use it as if electron moves along the band as a free particle like that. When you apply from external electric field or so on. But that really justified or that approximation or that experimental law, that means that works, or it can be proved.
Yeah. So sorry, I don't get you.
Yeah, that is it. For the when you draw band diagram, right?
Yeah.
And then if you apply the external field, then electron may move along the band, right?
Yeah.
Band means, when you draw, say, my understanding that band structure that you have the, say, hydrogen atom, then it has an infinite number of states, right? Hydrogen atom.
Understand.
Hydrogen atom has sp and so on, say n equal 1, 2, 3, and so infinite number of states, right? Hydrogen atom.
Oh, okay.
So I'm not saying any difficulty, just most elementary thing, okay? Hydrogen atom has a Bohr orbit, that's an infinite number of Bohr orbits, right? And if you have many hydrogen atoms, then one S-wave orbit electron may make transition to the next, atom and so on and so forth. That some kind of coherent movement may be the band structure. I understand, right? This is S band, P band, and so on.
Yeah.
But then question is what happens if you apply external force from outside? Whether electron on that orbit looks like the free electron or so, that's not trivial at all to me,
Yeah.
Right? Everything is in the bound state.
Yeah. Yes. So you mean the many pivotal bands in below had the formula wall?
Yeah, for example, if you consider single hydrogen atom, if you apply from outside force, then we don't see say any, maybe just a transition from S state to the P state like that. But electron in the S orbit does not make any movement like that, right? In a quantum sense.
Yeah.
But when it comes to the many particle system, then you treat as if electron electric forces working on the electron, and the electron moves just like the free particle along the band line. So I was wondering whether that there is a well-established rule, or just based on the experimental success and it works.
Oh, okay. So
maybe that's complicated. So it's getting complicated. So it's okay. Yeah, but later on, I'd like to ask you.
yeah.
Okay, thank you.
Okay. Thank you.